I'm Claude Alain, and I'm a scientist at the Rotman Research Institute. The research that I do primarily is on auditory perception and how the perception of sound changes as we get older. The example often that we take to illustrate the problem we're interested in is what we call the cocktail party example. So this kind of situation where you have a lot of people talking at the same time and you try to follow a conversation among all these co-occurring conversations. So the question becomes, how do you manage to segregate the conversation that you are interested in? What are the relevant cues? What are the part of the brain that might be important to sort it out this kind of auditory scene? And how does it change with age? Because one of the things that we know as we get older, we are experiencing difficulty in following a conversation, especially in noisy situations like in a restaurant or that sort of thing. To understand how we do that, we use different imaging techniques that allow us to look at the brain from various points of view. One technique is using EEG, like an electroencephalogram, and allow us to look at how long does it take for the brain to process certain kind of information. Another tool that we use is called functional magnetic resonance imaging, and this is a tool that allows us to see which part of the brain that might be involved while we try to understand speech in a noisy situation. And what we are currently doing or planning to do in the near future is try to see how these kind of tools or measurements of different measurement of brain activity can inform each other and help us to understand a little bit better how the brain works or try to solve this type of problem, which we call the cocktail party problem. The research that we've done using EEG allow us to develop new tools that allow us to measure hearing sensitivity in babies. Now, if you ask a baby to tell you whether he hears sounds or not, obviously a baby cannot tell you that. And there's maybe some behavioral measure that you can take, but it's difficult in some cases. But basic science on using EEG technique, for example, has developed these new measures that allow us to see how the auditory system is responding to sounds of various frequencies and so on. And that provides us with an objective measure of audiometry, if you wish, or hearing sensitivity in the babies. And this is also important not only in babies, but you can also use it in the case of patients who have a stroke, where they cannot really communicate in the case of aphasia. Basic science also in aging, for example, try to identify what are the problems that older adults cannot distinguish carefully, may help us in while we try to design hearing aid. If we know, for example, that they have certain problem in certain frequency range or in processing certain location, perhaps we can improve the algorithm, we can improve the tool to filter these sounds in a better way, and that can impact on how you design a better hearing aid. This is just an example of how studying neurophysiology, measurement of brain activity can lead us to develop a tool that can be applied in clinical practice. I'm Claude Alain, and I'm a Rotman scientist at Baycrest.